Welcome. This is Chuck Ridgway, Automation Technology Manager here at Horner. It's good to be back live after a few weeks away and some pre-recorded videos that we dropped for you on Tuesdays like we always do. And today our program is all about data parsing instructions in Cscape. So data parsing is a topic in which we're going to talk about one aspect of dealing with data in your logic program. So specifically, we're going to review some of the programming techniques and the logic instructions for parsing data. And parsing, when we talk about parsing, it's really the process of manipulating a string of data to extract and isolate one piece of the data. So let's go ahead and bring in Casey Gardner. How are we doing today, Casey?
Hey, not too bad, Chuck. How's it going? It's been a while.
It's going great. It's good to be back. Now, as we talk about data parsing today, what are some of the applications where data parsing is a really important aspect of the application?
I think one that comes to mind is definitely like RFID tag readers. Basically, when you're messing with those, you're reading a string of data, whether it's ASCII or a number of different types of data, and you're really trying to break it apart to see what the meaningful information is. It could be right there at the beginning, it could be at the end, or it could be in the middle, and you've got to find the data you need and associate it with like a part number or again a certain type or part identifier for whatever you're trying to use, and use it in your logic accordingly.
Yeah, so that's similar to what you would do with barcodes, right? If you're scanning in a barcode, often you're going to get more than just one field at a time when you scan them in. Sometimes not, but you often do get a big string of data. Another case that we're going to review today is the case with mobile applications or any application that has a diesel engine, for instance. All those applications use a protocol called J1939 that's supported by the OCS. And in that protocol, it's pretty typical for 8 bytes of data to be dumped at a time to the network, and the data you need could be buried within those 8 bytes. So that's another case where you've got a chunk of data, you've got a piece of data you need to extract out of there, isolate it, put it in its own dedicated variable, that sort of thing. Okay, so we're going to cover data parsing today. Now, during our program, Casey is going to be manning the chat. So this is another live stream. So if you're watching live, you can go ahead and chat your questions in. Casey will either answer them or he'll save them until the end. Now, if you're watching this on replay, which a lot of you do, you can still ask questions. Just do it through the comment section, and then in non-real time, we'll get that question answered as soon as we can. Okay, let's go ahead and get started. All right, so here is the outline of our program today. We're going to cover, of course, what is data parsing, and we're going to cover some of those useful instructions for data parsing. Those will include things like the bitwise and, shift left and shift right, and also we'll talk about the multi-shift. We'll go through some different programming examples, and we'll do a live demonstration as well. Okay, let's dive in. Okay, so what is data parsing? Well, let's just start with a general definition of the word parse, not a word we use very frequently, to be honest, in the English language. If we take a look at the dictionary, it's going to say, okay, to parse is to examine or analyze minutely. In grammar, we would kind of go back to 8th grade English, where we might be breaking a sentence down into its parts. Oh my, I think I'm getting shivers just thinking about that. In the computing world, to parse is to take data from one format and transform it into another format. But today, when we talk about data parsing, we're going to be talking about manipulating a string of data to extract and isolate one piece of the data. That's really what we're going to be talking about today when we talk about parsing. All right, so why do we need to parse data? Well, this is a lot of what Casey was talking about and a little bit of what I was talking about before the program started, and that is sometimes the data we want is buried in a larger string or bucket of data, okay? And to extract that data, it can involve a number of operations. It could involve getting rid of extra data that is undesired. It could involve moving the data that you want around so it can be interpreted properly as an integer value or a floating point value, whatever the case may be. It can also sometimes involve converting from one data type to another. So again, there are a number of operations you may need to do on your data depending on the specific situation. All right, so now we're going to start talking about some of the instructions that you could probably use in the parsing operations. Let's start with the bitwise AND. Now in Cscape, there are a number of what are called bitwise operations which deal with data at a bit level. And when you're parsing data, grabbing data out of a big bucket of information, very often you do need to operate on a bit level to move things around the way you want or to clear the data that you're not interested in. And clearing the data you're not interested in is what the bitwise AND function is all about. It's the easiest way to clear unneeded data, which we sometimes call masking off. Now, what this instruction does is it performs a bit-by-bit AND function on the binary value of the two inputs. Okay? Now, the first input almost typically, or almost always, is going to be the variable that you're operating on. All right? And the second input is going to be a constant that's going to be ANDed with your variable. And the reason you're doing that is because depending on the constant that you select, it's going to effectively mask off different bits within that word or double word that you're operating on. So for instance, for all the bit locations that you want to keep, you're going to put a 1 in the binary location for that masked value in order to keep that data. For all the data locations you want to throw away or clear or set to 0, you're going to put a 0 in those locations in the mask value. Okay, let's take a look at an example. I think looking at an example is going to make it easier to visualize this. Okay, so let's say that we have a variable R1 that contains 8 bits of desired data. All right, but remember, word type variables, and when we say %R1, we're talking about a word type variable typically. That's 16 bits worth of data, not just 8 bits. And let's say in this example, the 8 bits that we want or we need to deal with are right smack dab in the middle. They're not in the lower 8 bits, they're not the upper 8 bits, they're right in the middle. Okay? So we're going to use a bitwise AND function to get rid of the data below and above the data we care about. So if we take a look at the bottom there, you can see the ends in red are the 8 bits we care about that happens to be smack dab in the middle of the word. And then there are 4 bits at the bottom and 4 bits at the top that are really unneeded or undesired. We want to get rid of those or at least clear those to zeros. Because remember, they aren't necessarily starting out as zeros, those values in yellow, those X's in yellow. They could be other data, and they probably are other data. It just happens to be data you don't care about. Okay, moving along in our example, again, redrawing R1, what it looks like on a binary level there with the yellow X's undesired data and the red N's the desired data. We're going to create a data mask where the top 4 positions and the lower 4 positions are all zeros because we don't want that data, and any data ANDed with 0 is 0. And in the middle, we're going to put 8 consecutive 1s because there are 8 consecutive bits that we do care about, and any data ANDed with 1 results in whatever data you started with. Okay? So R1 and that data mask, which is the binary pattern you see on the screen, which happens to convert to a decimal value of 7698. So when we take R1 and we AND it with 7698 decimal, our result is the data we care about in the center with zeros at the top and zeros at the bottom. Now, the data, the ends, if you will, are still probably not where we want them, but at least we got rid of the data we didn't want. All right, so that's what the AND can do for us. It doesn't get rid of unwanted data completely, or it doesn't necessarily move the data we want to keep around, but it does get rid of the data we don't care about. Okay, so that's the bitwise AND function. But that's just one of the functions you may have to use in a parsing application. Let's take a look at another one. Another one is shift left and shift right. So this is an instruction that is strictly used for moving bits around in either a word or a double word type variable. Okay, and it's definitely the easiest way to move those bits around, either move them down, move them up, left or right effectively, if that's what you need to do in your parsing operation. Now, shifting left moves the binary data bits up. So bits become higher in significance. Any bits that are shifted above the most significant position, the 16th bit effectively, anything shifted above the 16th bit is discarded. Okay? You also got a shift right instruction, and it moves binary bits down. So therefore, all the bits become lower in significance, and any bits that are shifted below the least significant position are discarded. And again, you've got two inputs. The first input is the variable you're going to work on. The second input is the number of positions that you want to shift, whether it's left or right, depending on the instruction you've selected. All right, let's take a look at an example for this guy. We're going to actually pick up where we left off with the previous example for the AND function. Because if you remember, where we finished up is we had register 11 with 8 bits of data that we cared about in the center of the word, but at least we had cleared to 0 the least significant 4 bits and the most significant 4 bits. But now what we need to do is we need to align those 8 bits we care about with the least significant position, because ultimately, let's say that's a decimal value from 0 to 255, and we want it to be interpreted properly as a decimal value from 0 to 255. If we leave it there in the middle, it's not going to be interpreted as a proper decimal value. It's going to be multiplied by like a factor of 32 or something. So that's definitely not what we want. Okay, so by doing a shift right instruction where the input is R11, N is 4 because we want to shift right 4 positions. The end result for our output variable, which we've assigned as R12, is going to be, we're going to have the 8 bits we care about aligned in the proper position. Okay, so that's the shift right. You can also use the shift left to shift the other direction in those applications where that's what you need to do. Shift right is going to be used more commonly, though, I would say. Next, let's talk about the multi-shift function, because so far, the AND instruction and the shift left and shift right instructions are bitwise operations that can only operate on word type variables or double word type variables. What if you've got a bucket of data that's a lot bigger than that and you need to operate on a bigger bunch of data? Well, multi-shift can be handy for this. Okay, the multi-shift function is really the best way to shift data around when more than 2 words of data are involved. So the example that Casey gave for the RF tag reading, you're probably going to have, let's say, 30 or 40 characters that you're reading in. Heck, it could be 128 characters or even more in some cases. And so you're going to have to deal with many more words of data than what you could do in just a shift left, shift right, or a masking and type instruction. Okay, however, the multi-shift function, there's more to it. Now, I will say that we did have a complete video on shifting data on shift registers. So this is covered in a lot of detail in another video as well. But specifically as it relates to data parsing, let's take a look at the input values and output values for the multi-shift function. First of all, the source is the start or the first variable in your array of data. Okay, so if you have 20 words of data starting at R1001, then your source would be R1001. Length is how many elements in the array are there. Now, with the multi-shift function, it works with either bits, bytes, words, or double words. So you can select the form that's the most convenient for you. Now, if you're dealing with characters, from a barcode reader or something like that, it's 1 character per byte. So it might be the most convenient to do a byte style multi-shift. So the example I'm going to show today does exactly that. So the length is going to be the number of elements in the array, or the number of elements in the multi-shift based on the type that you select. So if you've got 16 consecutive words and you selected a byte type, that would be 32 bytes. Direction is the direction you want to shift. Remember, with the shift left and the shift right instruction, we had 2 separate instructions. With the multi-shift instruction, you have a direction input, which determines whether you're going to shift left or shift right. If you want to shift left, you make that a variable that has a value of 1, a binary value with a value of 1, like always on. If you want to shift right, you would assign a binary value with a value of 0, like always off, for instance. In is the data to shift in. Now, if you're dealing with characters, it's probably going to be convenient to use a variable that has a value of 0 to shift in, because what you'll be shifting into your array of characters is the null character, okay, ASCII null or ASCII 0. So that's just convenient. Although in a lot of cases, the specific data value you shift in isn't all that important. You're mainly interested in the data that's already there that you've shifted around to a new position. And then out is the data that gets shifted out. And again, at least in this particular case, for this instruction in this application, a lot of the times the variable you assign to output isn't really important to you. Okay, let's move on to our example. Okay, so let's say that we have a multi-shift that we're going to use here to help us deal with a series of registers, 16 consecutive registers, that contain a string of 32 characters from a barcode. Okay, so again, when you're talking about ASCII characters, they take 1 byte per character, and there, of course, are 2 bytes per word. So if you have 32 characters, you need 16 words. Now, in that string of 32 characters that we're getting in from the barcode scanner, the 12th through the 20th character happens to be the part number field that we're interested in. So we want to isolate that field and create a separate variable for part number. So that's the application here. So our source of the data is going to be register 101 because that's the start of our data. All right. We've decided, because we're dealing with characters, we're going to do a byte type multi-shift because that's the most convenient way to deal with characters, is on a byte level. The length, therefore, is 32 bytes, which is the equivalent of 16 words. Now, how many positions are we going to shift? So we've said that that part number field is the 12th character. That's where it starts, at least. Now, why wouldn't we shift 12 positions? Well, because if we shift 0 positions, the first character is in the first position. So if we want the 12th character to be in the first position, we need to shift 11 positions. So that's why we're setting our n, or our positions to shift, to 11. Now, which direction do we want to go? Now, we could make it work either way, but in my case, I typically like to move the data I'm interested in down to the first position. So therefore, I'm going to assign always off, or a binary value of 0, to the direction. On the input side, because I'm dealing with characters, I'm going to shift in zeros at all the positions I'm shifting into. And on the output, I'm just assigning a junk variable to it because I really don't care about the output of this instruction. Okay, so that's my multi-shift. Let's take a continued look at this example. So let's say in the top there that that's what our barcode data looks like in ASCII before we do any kind of shift on it. Okay, so you can see we've got SN1011, that's probably containing the serial number. We have a carriage return character that I'm showing there on the screen. We have a 4-digit numeric field followed by the start of the part number, which is HE-XC1000. After that, we've got a carriage return, a date field, a couple more carriage returns, and a line feed. So again, the information we're interested in starts with that HE-XC1000. That's the information we want. So if we shift 11 places, now instead of SN1011 being at the beginning of our data, now the part number we're interested in is at the beginning of the data. Now, again, just like with the AND instruction, we haven't done the entire job here. All we've done is moved the data we care about to the first position so it's easier to work with. We're still going to have to do subsequent operations to move the data from this bank over into its own variable. So we'll use instructions such as, for instance, a byte move instruction, which you can use to move the 9 bytes of the part number over into its own variable. We can also use a byte move instruction, for instance, to move a terminating ASCII 0 character to the end after the part number. Because think about this. We've got a 9-digit part number, so 9 characters. Now, those 9 characters will take 9 bytes for storage. That means basically 5 registers worth of data, which is 10 bytes. So we've got that leftover byte at the end. We want to fill that byte with ASCII 0, which is null. so that our part number will be properly interpreted everywhere else in our program. Okay, so we'll use, again, a byte move to move the 9 bytes from this string over to its own variable, and then we'll use another byte move of a constant of 0 to fill in the end of our part number variable. Okay, so that is the multi-shift type instruction. All right, let's go ahead and do a couple of demos. And let's start with an example where we do some numeric parsing. All right, so we're dealing with numbers, not ASCII characters, but we're dealing with numbers, okay? And this is an example that we might see in a J1939 application. And once again, J1939 is a protocol, a CAN-based protocol supported by the OCS, which is used effectively on any automated device that has a diesel engine. So it could be a compressor, it could be a diesel engine for a mobile device, it could be a diesel pump for a remote irrigation application, a whole variety of different things. Let's look at an example that you might see with J1939. Now, the way J1939 works, and we'll do another future video on J1939 with all those details, but anyway, with J1939, it tends to effectively have a bucket of data that is called a PGN, and each PGN has a number associated with it, and it also has a description. So let's take a look at PGN 61444, which is called the Electronic Engine Controller 1 parameter. And buried within those 8 bytes or 4 words are a whole series of different parameters. There's torque mode, torque resolution, the actual torque, the starter mode, the total torque demand, all kinds of data packed within that one particular message, which is 8 bytes, or once it gets into the OCS, 4 words long. Okay, now dead in the center in bytes 4 and 5 is engine speed in RPM. Okay, or at least it's scaled for RPM. Now what you'll notice, if we take a look at the next slide where I've highlighted it in red, is you'll notice that the least significant byte for engine speed is located in the upper byte of register 202, as we've mapped it here. And the most significant byte of engine speed is in the lower byte of register 203. So where it resides or where it comes in, it's not in any condition, if you will, to be interpreted as a proper 16-bit decimal number, which is what this engine speed is. It's a unsigned integer from 0 to 65,535, which is scaled to RPM. Specifically, you need to take that value in those 2 bytes, interpret it as a decimal value, unsigned, and then divide it by 8, and there you'll get your RPM value. Okay, so how would we do this programming-wise in the OCS? How would we deal with this data? All right, let's go ahead and head over to Cscape. And let's take a look at how we might do that. Now, I'm not covering how the data came in or anything like that from a J1939 standpoint. I'm assuming the data is already here, and we are going to just handle the data to get it converted over to the format we need. So really what we need to do, if we go back again and take a look at that slide, really what we need to do is we need to shift the bytes around so that they are next to each other in the same variable. That's really what we're talking about here. Okay, so what I'm going to do strategically is I'm going to take a look at register 202 as a double word. Okay, again, going back to the slide, you can see that register 202 is the first register that contains some of the data we want. Register 203 contains the rest of the data we want. But again, there's extra data in there that we don't want to deal with. So going to Cscape, what I'm going to do is I'm going to use the shift right instruction. Now, why am I using the shift right instruction? Well, first of all, I'm dealing with a 32-bit value here. I've been able to isolate the data I'm interested in into a variable that's 32 bits long. That means the shift left and the shift right instructions can be used. Okay? So what I'm actually going to do is I'm going to shift right, or effectively shift down, 8 positions, 8-bit positions. so that the data I'm interested in gets moved down effectively 8 positions for bits or 1 byte. All right, and then I'm going to take that result and store it in a new variable that I've assigned as to register 211 in this case. Then the last thing I'm going to do, all right, this isolated the data I needed. The last thing I'm going to do is just convert it from its decimal value over to RPM, which is just a math operation, which is effectively divided by 8. So what does this look like? I created a screen that we can take a look at that will show us what this looks like. At the top there, I've shown 4 word type data fields that are showing the 4 words for PGN 61444. So just looking at those data as individual words on the OCS, you can see those are the decimal values that we're looking at for those 4 words. But the data we're interested in, again, is buried in a couple of bytes that are not falling on word boundaries. So after I did my shift, my result in register 11 was a value of 16,000. Okay? And then at the bottom there, that's my result after I divide by 8. So in this particular case, all we had to do was take a look at the value we're interested in as a double word, shift it down 8 bits, okay, or 8 positions, and then look at the resulting value as an integer. So this, we're looking at register 211 as an integer. Look at the resulting value as an integer, divide it by 8, and then we get our result in RPMs. Okay, so this was actually a simple one. It looked like it was going to be a mess because the bytes weren't aligned and all those sorts of things, but literally all we had to do was use a shift right instruction, looking at the data as a double word, shift it down 8 bits, and then look at that result as a single word, and we're done, except for dividing by 8 to convert to RPM. Okay, so that was ending up being a relatively simple one. Not all parsing operations are highly complicated. Some of them are extremely simple, and this one turned out to be pretty simple. Let's go back and now take a look at the next example that we're going to cover. And this is an example where we're going to do some parsing of ASCII data. So this is a barcode example, and we're actually going to go back to the example that I kind of showed in the slides. And that was this example right here, where we've got a bank of 32 characters stored in 16 registers that consist of a barcode that we've scanned in, and we need to extract or isolate or parse the part number field. Okay, so let's take a look at what's involved in that particular act of parsing. So let me go back to Cscape. Okay, so what do we got going here? All right, so let's just start in this line here. We're doing several operations in a row. What we have in this example is we have a barcode scanner which is dumping the barcode data into register 81 through 96. So there are 16 consecutive registers where this barcode ASCII data is residing. So that's the direct buffer where we're reading in the data. And again, in this session today, we're not talking about how the data comes in. We're just assuming the data is already there. We have a good barcode and serial data type webinar live stream if you're interested in going back and watching that one to see a little bit more about how the data came in. Okay, so we've got 16 consecutive words that contains the raw barcode data. The first thing we're going to do is we're copying it into a new set of registers where we can work on it. We can shift things around and those sorts of things without impacting the original data as it's received. Okay, so I'm moving that into register 101 through 116. Now, because we're talking about data that's bigger than a byte or 2 byte or a word or 2 words long, we're going to use a multi-shift to actually move the data where we want it. And if you remember when we talked about it, the part number data we're trying to isolate is in the 12th character location. So we've created a multi-shift, byte style multi-shift, which starts at register 101 is where we've got our working location for the data we're dealing with. It's 32 bytes long, or 16 words. We're shifting 11 bytes so that we have that 12th byte in the first position where we can see it. The direction we're going is we're shifting everything down or right. Okay, so we need an always off here in this field. And then the data we're filling in, or the data we're going to be shifting in every time that we shift in, is a register 121, which is named null character. That's just a register with a value that always has a value of 0. That's all that is. That just makes it simple when we're looking at ASCII data to have null characters where we're not interested in data. Okay? And then the output of our shift register is just a junk variable that we never care about, but we have to assign, which happens to be register 122. So taking a quick look at the data as I just described it, there we go. So that's what our multi-shift looks like. Okay, now when we get done with that, just like I talked about in the example in the slides, we don't have the data completely isolated. We just have it in the first position, register 101, where it's more convenient to work on it. So now what we're going to do is we're going to do a block move operation, and it is a byte type block move where, again, 1 character per byte. We've got a 9 character part number. So we're going to move 9 characters or 9 bytes from R101, which has just been shifted, over to a new variable called part number, which has been assigned to register 141 through 145. Because remember, for 9 characters, that's going to take up 5 words. So that's 141 through 145. Now that we've done that, the only thing left is to deal with that 10th character, right? Or that 10th field in those 5 registers. And we want to write that as a 0. So what we're going to do is we're going to get a little bit clever here, and we're going to do another byte move, but we're moving a constant value of 0. And what's important is we need to move it into the upper byte of the 5th register that's storing that part number. So the part number starts at 141. The first character of the part number is going to be in the least significant byte of 141. The second character is in the most significant byte of 141, and then so on and so forth until the 9th character is located in the least significant byte of 145, and the most significant byte of 145 is, we don't know what that value is. And that's the byte we want to assign as a 0 to, just to be sure that it's a 0 value, which is ASCII null, which is a great terminator from an OCS standpoint for an ASCII field. So when you use any other kind of ASCII instructions in the OCS instruction set, it looks for a 0 after the ASCII field is complete, knowing that that's the end of the ASCII field. Okay, so that's the parsing that we need to do for this particular example with a barcode example for ASCII data. All right, now let's take a look at what this looks like on the screen. Okay, so back to the OCS. Let me go home, and then let's take a look at the ASCII example. At the top there, what you see is the barcode data just raw as it comes in. So you can see it there, starting with the serial number field, SN1011, and then that little box you see there, that's a carriage return character. It can't really be drawn any other way, so it's just drawn as a box. And then after that is a 4-digit numeric field, 1, 2, 3, 4, and then you've got the part number that starts. Now the second field, we're taking a look at the data after we shifted it. Okay, so that's the data that starts at R101 after it's been shifted. There you can see our part number is right where we want it at the beginning, but we still have a carriage return and some other data at the end that we want to get rid of. So the way we're going to do that is, again, through our byte move function that moves the first 9 characters over to a new variable and then sets a 0 at the 10th character. So the OCS knows, okay, that's a complete ASCII field that's 9 digits long, and the 10th location is just the terminator of 0. So that pretty much is the material that I wanted to cover today. So let me go ahead and bring in Casey Gardner. Okay, Casey, so that's parsing. That's some examples, some instructions that can be useful. Any questions that came in during the broadcast?
Yeah, Don't think so. Let me check here last minute, see if there's any stragglers that have any. But
And again, while Casey's
Nope.
checking that, and I don't think he's found any questions, while he's checking that, just a reminder, if you're watching this on replay, don't hesitate to ask questions through the comment section. We'll get them answered as soon as we can. Okay. Looks like we're good. All right, so I do want to remind you that every Tuesday, we're here at 2 o'clock with another live stream. Always live when we can. So far this year in 2021, we've been able to post a video every single week. We are certainly looking to continue that through at least the end of the year. Most of them have been live, only a few pre-recorded because of, travel type obligations and those sorts of things. So again, whether you're watching them live, you're watching them on replay, don't hesitate to check out the content that you're interested in based on what you're working on with your current project. Also, I want to mention, don't forget to subscribe to our channel. That way, every time we go live or every time we post a new video, you'll get a notification, provided, of course, that you hit that bell as you subscribe. And don't hesitate to join us next week, where we have another new video coming your way. I believe that video is going to be regarding different analog filtering techniques that you can use to filter your analog data so you get the stability and the response and the information you're looking for from your analog sensors into your application. Okay, so keep your eye on our website as well as for our November newsletter that will announce specifically, I believe, the 4 additional topics that we have for November. Once again, thank you for joining us today, and stay safe out there.